yeah. So it's directions that we, okay, yeah, it's directions that we want to use to make a step in the first order method. So then clients are asked to send these vectors back to the server, and server just averages them and makes gradient descent type step. Okay, and in this setting, we assume, okay, maybe it's a good time to pause, and if anyone has questions, yeah, you can ask me.
I think it's been pretty clear.
Okay, good. Then in here, I assume that all clients, they honestly compute the stochastic gradients, meaning that all of these vectors are on average true gradients. But what if some clients, they are faulty, or they maliciously join the training protocol and they maliciously send something incorrect, like add some bias to the gradients. Let's assume that everyone are honest workers, compute stochastic gradients honestly, but one client sends some arbitrary bad vector. This vector can make our average direction also arbitrary bad. And even one step like that can destroy the entire training. So, and this situation typically appears in this collaborative training. Yeah, even if clients are not malicious, they might be faulty. And this can destroy the entire training. So to address this issue, many researchers worked on the area called Byzantine-Tolerant optimization. So by the way, those guys essentially they're usually called Byzantines. So it's the term goes back to the systems literature and to the term Byzantine attacks. You can search and read the story in Wikipedia why we use this name. But by Byzantine, people often assume some clients that can send arbitrary, like they can send anything instead of what is required by the protocol. And moreover, it is assumed that they know everything about computations of others. So two assumptions. They can send anything and they can know everything about computations of others. So you may ask me, like, why do we need to assume that these Byzantine clients, they know everything about, let's say, these vectors? Indeed, it seems to be a very strong assumption, in many cases unrealistic. But the main motivation is that if we can design a method which is robust against such attacks, then it will be robust against any kind of attacks, even when Byzantines do not have any knowledge about other computations. This is the main motivation. Okay, and then also what's important to say is that we need to refine a bit the problem formulation, because previously I didn't say anything about what are those functions fi. Can they be arbitrarily heterogeneous, arbitrarily different? And it's, after thinking a bit, it becomes very clear that it's impossible to solve a regional problem if we allow these local functions to be arbitrarily heterogeneous, because in this case we cannot distinguish between honest and Byzantine workers. Also, even when we assume some bounded heterogeneity, let's say in terms of the gradients of those functions, then we immediately, then it's possible to show that we can achieve only some neighborhood of the solution. This was actually shown in this paper. And therefore, in this paper, in our paper that I'm presenting, and also in this talk, we will assume that all functions are the same. So essentially, it means that clients have access to some public data set, and they just want to collaboratively train some large model on this data set. So the data is public, And it means that they can sample Xi from entire dataset, which implies that all functions are the same. Okay, so next, it's important to say a few words about the number of Byzantines, because of course, if you have a majority of Byzantine workers, then in this generality, we cannot do much. If Byzantines form majority, we cannot understand, we cannot distinguish between good and malicious peers. So we will assume that our set of workers is split into two groups, good or honest workers and Byzantines. And we will assume that number of Byzantines workers is smaller than half of the total number of workers, which is a reasonable assumption. Also, let's say at iteration k, workers send some vectors to the server, and for good workers, we assume that they send unbiased estimates of the true gradients. We can assume bounded variance. We can assume other assumptions, but for now, for simplicity, let's assume bounded variance. So on average, it's not too far. And about Byzantines, we will assume nothing. They can send anything, even something that depends on computations of other workers. And in this scenario, there are multiple approaches how we can solve this problem. First idea that comes to mind maybe is to ignore all collaboration and just let the good workers solve the problem independently. But of course, this will be too slow because the whole idea of collaboration vanishes. Another idea is just to blindly use this averaging in the hope that it will converge somehow, maybe not to a very good solution, but to some solution. But of course, in this case, even like one Byzantine worker can break the entire method. And mainly because this averaging, it's not a robust mean estimator. So because of this reason, like many people, many researchers and many papers in the literature, they focused on fixing this averaging. And a very good and widely used idea is to replace this averaging with some robust aggregation rule. So, and just plug in it in the same SGD type update. So it's a very natural idea and sounds reasonable. So let's see what was done. I will provide some examples. So many papers, they worked on developing different robust aggregators. For example, aggregators such as geometric median, which searches for the vector, which minimizes the cumulative distance to the points, GIKs. Or coordinate-wise median, so essentially we compute median for each coordinate, or equivalently, we minimize sum of L1 norms. Or more sophisticated estimators, and actually I just named a few. There exist much more of that type. But the whole idea is to somehow robustify the mean to enforce some robustness to the outliers. This is the main idea. Okay, but then in 2019, Baruch et al., they showed in their NeoRIPS paper that simply using these robust aggregators, even like team mean, some other aggregators, this will not give you good results. And in particular, they provided an example of an attack such that SGD without any defense, like with pure averaging, it works much better than SGD with defenses. So clearly there is something going on there. So parallel SGD is more robust than robust methods. We want to avoid that. And partially this was the reason for that was that there was no formalism for robust aggregation. So, and this formalism was introduced by Karim Reddy et al. In their ICML 2021 paper. So they say that basically this aggregator is robust, GK with hat, if it approximates the ideal average. So ideal average is just average over good clients up to this error, which is proportional to delta, which is a ratio of Byzantines. This is a reminder. Delta is assumed to be smaller than some delta max. Delta max here, it can be used in the construction of robust aggregation. And sigma squared is just pairwise variance between good workers. So this definition makes sense because the fewer Byzantines we have, the tighter approximation should be. Also, if the variance between good workers is small, meaning that they are well concentrated around each other, then it should be easier for us to, like, in some sense, filter out Byzantines. Yeah, so maybe there are some questions about the definition or setting.
Yeah, do I get it right that the sigma works as a measurement of heterogeneity, effectively?
Yeah,
I mean, how different are they? Mm-hmm.
In a sense, this sigma, it's, yeah, I mentioned that we will assume that data is homogeneous, but it measures heterogeneity of vectors itself, GIK. So it's natural since they're stochastic, even if they're unbiased estimators of the same, even if they have the same mean, still they will not be the same if you sample them. So the larger sigma is, the more, let's say, the further from each other they will be with high probability. So this is it. So you can think about sigma as the smaller sigma is, the simpler problem is. So because even individual, in this case, even individual gradient becomes already very good estimator of the full gradient. Or any other questions? Okay, so yeah, it's just formalism, and then they also showed that, I will skip this slide, but they provide an example that this so-called middle seekers like median and CRAM and other estimators, they are not satisfying this definition. And they also show that this definition is actually something, it is up to a constant, it's the best we can hope for. They show that for any aggregation rule, one can come up with such set of vectors that we have this lower bound. So delta and sigma squared in this formalism, they should be there. Okay, so, and then they proposed some aggregation rule, which is called centered clip. You can skip this. You don't need to understand this formula. I have some nice picture. Okay, here it is. This is iterative procedure. So it tries to build a sequence of centers, VL, these purple dots. So you can interpret this VL as a center of the ball with a radius tau L. And at each step, we check points GIK. So in this case, we have n equals 3. So we have red, green, and yellow. And essentially what we do, we project them on this ball. And after that, we just average them. And this will be our new center of them. It will be VL plus 1. It will be average of red, green, and yellow. So it will be somewhere here. So that's it. It's just, okay, actually somewhere here. So this is the whole idea about centered clip. And they have some nice proof showing that this procedure, it converges to something, and essentially it gives you this formula. So after a long number of iterations, you will get the desired error proportional to delta sigma squared. Okay, so it's just a technicality. And then natural question arises. Okay, now we have robust aggregation rule. Let's just plug in it in parallel SGD and replace averaging step with this centered clip. What should, like, it should work, right? So it's everything we did was a natural step towards the success, let's say. But in the same papers, they show that no, it's not enough. Actually, what they proved that any permutation invariant algorithm, it will not converge to arbitrary good solution asymptotically. What does it mean? So imagine you have computations. So here for the first client, we had the following computations of stochastic gradient. Here are stochastic gradients for the second client and for the nth client. And imagine I permuted those vectors between clients. So meaning that I just applied some random permutation of these vectors in each column. And if my output of the method doesn't change, then we call the method permutation invariant. So for example, if I permute here those vectors, the output will not change because in center clip, it doesn't matter like in which order we put stochastic gradients here. So those kind of methods are permutation invariant, and you can already see that if you apply any aggregation rule to the collection of points, then it will be also permutation invariant. And it turns out that if the algorithm is permutation invariant, then there exists a simple, strongly convex problem such that this lower bound holds. So we cannot hope for convergence. And what they proposed to do to break this permutation invariance, they proposed to use client momentum, like standard heavy ball momentum or Pollack momentum, as it's called in the literature. And you can think of it as a memory. You use some stochastic gradients from the past, so it constructs a very good approximation of the true gradient in a sense. So you can think of it as variance reduction in a sense. So essentially, by doing momentum, you decrease. Sorry for jumping. You decrease this, but you will use different vectors here, not GIKs. And then for this method, so instead of using stochastic gradients, they use client momentums, and then the resulting method, as they proved, converges as this. So it finds epsilon stationary point under some assumptions which are not like important for now. They proved this complexity bound. So sorry, I'm working on optimization, so that's why I'm usually thinking in terms of complexity bounds. But to explain it for non-optimization oriented audience, so perhaps some listeners are. So here it is. We have two parts of the complexity bound. The first part is standard, like it corresponds to the parallel SGD in the ideal case when we don't have any Byzantines. And the second part, it depends on the fraction of Byzantines, delta, and it is almost the same as the second term here, but instead of 1 over n, we have delta. Delta is always larger than 1 over n if you have at least one Byzantine. All right, so and then let me briefly mention what was our contribution, because building on that, it's very easy to explain what was our contribution. So we focused on the following thing. So this result is very nice. It was, we relied on that paper a lot. By the way, it's very good read. I highly recommend that paper. But the key limitation there is that the method relies on the usage of parameter server. So if we don't have this parameter server, if we want to make method scalable, then it's unclear how to solve the problem. So yeah, and with this motivation, we started working on this project. And yeah, as I said, if you have parameter server architecture, it's simple and widely used, but not scalable. Meaning that if you have large number of workers, the communication is a bottleneck. And there exist various approaches how to address scalability. For example, one can use all reduce. For example, butterfly all reduce. Here it is explained. Here it is explained schematically. Let's say, what is the main limitation here? The limitation is that a server needs to receive and send n vectors at each step. And so meaning that this machine is overloaded. But in the approaches using all reduce, all machines, they communicate only all of one vectors. So for example, here we have 3 workers. They want to compute average of x1, x2, x3. The idea is to split each vector into 3 subvectors corresponding to each worker. And then the first worker will be responsible for averaging the first part, second worker will be responsible for averaging second part, and so on. And then each worker sends to the first one first parts, and so on. And the first worker sends second part to the second worker, third part to the third worker. So it's everything is indicated by colors. After that, they compute average and broadcast it back to all clients. In the end, we have exact average on every client, but in total, each worker communicated just in terms of information, just all of one vectors. But if some worker is faulty or Byzantine, it will damage the entire computation of the corresponding part. So it's not robust. And also there are gossip-based approaches. I will skip that one because it will not have much time. Yeah, so by the way, how much time do I have?
I think 15, 20 minutes should be good.
Okay, I will try to wrap up quicker just to have more time for the discussion. Okay, so now imagine we don't have a server, but we have Byzantine clients. So what should we do? How to modify, maybe how to adjust existing approaches. So in our paper, we focused on all reduced type protocols, but it's also important to have a look what was known before. Basically, previous approaches, they used either full gradients or they were based on gossip-based protocols, but in theory, those methods, they worked worse than one node SGD. So since we wanted to have strong theoretical guarantees, since we wanted to have some benefit of collaboration, we needed different approach for our purpose. And our main idea is based on the modifying butterfly all reduce that I already explained. So naive idea. Let's introduce here, instead of averaging or summation as it's indicated, let's use a centered clip from the previous paper. So very intuitive, like very natural step, but of course it's not enough because if, let's say, the first client is malicious, as I said, then this part, we don't have a control over this part. It can be anything because only this worker saw the first parts of all other workers, of vectors from all other workers. So meaning that this guy can be arbitrarily bad, and it can be even different for different workers, and it can again spoil the convergence. And the central idea behind our method is, like, I would say it's the main idea of the paper, is to design the method in such a way that all intermediate steps are verifiable. And if needed, we can check computations after the communication round. So, but to achieve that in decentralized, I mean, in the setting without parameter server, we need many intermediate steps, like to ensure that we can verify that computations were correct. So first of all, we assume that initially we have some, that stochastic gradients are computed using some seeds for pseudo-random generator. And this information is public, meaning that at each step everyone can calculate the sample which was used for computation of stochastic gradient at each worker. So in general, it means that computations are verifiable. And also another idea how to use this check of computations. At each step, we will use the clients are using some joint pseudo-random number generators that in order to select to pick random workers for computations for the checks of their computations, and in such a way that they do not know whether they will be checked or not before the communication round. So of course, if Byzantines knew in advance that they will be checked on the next round, they would compute everything ideally, like without any deviations from the protocol. So it's important to do that in such a way that they don't know in advance. And yeah, this is the main idea. And another technical idea is that we should design a method in such a way that at each step, the maximal harm from Byzantine attack is bounded. So we cannot just, even if we didn't check some Byzantine client who introduced some shift or bias in our update, it will not destroy the convergence. So, and then they can have and then the rest is just just technicalities. You just need to notice that in this setting, if we construct such method, number of protocol deviations by each Byzantine, it's bounded with on average. So it's bounded on average. So and this potential harm is also bounded. So bounded number of bounded shifts during the training. So, and until we find out. And this is the main idea. Okay, and then of course there are many technical steps. I will quickly mention all of them. So the main difficulties in this butterfly all reduce is that let's say if worker one is Byzantine and it's responsible for the first part of parts of vectors, then only this worker saw A2 and A3. I mean, except, yeah. So for example, this worker doesn't know about A2 and A1. So this worker cannot verify, cannot easily verify those vectors. And yeah, also, yeah, another thing that they can collude, so they can jointly, in between themselves, they can send anything what they want, and it will be problematic to check that. So to resolve this issue, we ask, like in our protocol, we ask every client to submit hashes of the corresponding of the JS part of their vectors. And by hash, we mean some function which is easy to compute, but hard to find any element of pre-image. So it's knowing GIKJ, it's easy to compute hash and to get this number. But knowing this number, it's hard to find such vector J that hash of J equals CIJK. Okay, and then knowing hashes, we can, when we check computations, we can identify whether it was good or not. If hashes coincide, then computation was good. But unfortunately, this is not enough, because Byzantines, they can send hash of the true stochastic gradient that was supposed to be computed, but use something different in computations. So to avoid that, we look closer in this centered clip aggregation rule. And essentially, one might notice that this iterative procedure is just a fixed point method for the following equation. So we're trying to solve, to find such vector GJK hat such that this equation is satisfied. But unfortunately, this equation only worker J can check, because only worker J knows about all of these factors. So to address this issue, we introduce random projections on random directions, and we generate this random vectors to check this equality. We generate this random vectors ZJK, again using a joint pseudo-random number generator. And we ask all clients to submit these numbers S and norm. So far there is some communication and computation overhead, but it's not that significant. And then when it makes easier to verify the computations, but again, even if the following situation is possible. Some Byzantines, they can jointly talk to each other and ask them and somehow send those numbers in such a way that this equation is satisfied. So to prevent that, we have additional parameter delta max. So essentially, this is maximal threshold that we can have, the maximal bias. And after each step, we ask every client to check the norm of the difference between the aggregation and their part and use majority vote. And this is exactly what bounds the bias of each attack. So to put all ideas together, so we use center clip for robust aggregation. Then we use hashes and norms and inner products along random directions to guarantee that all violations can be revealed either on the fly or during the checks of computations. And we also bound the bias of like this here in order to bound the power of each Byzantine attack, even if we didn't select the client for that. And then we randomly pick workers to check their computations. This is needed to identify and ban Byzantines. Okay, so this is the whole idea. I will skip this pseudocode, but because it's a bit long. But I just, what you need to remember is just this scheme. So we modify all reduce in such a way that each step now can be checked after, and also we add this threshold to bound the power of the attack. Okay, I will skip this one. And also, what is important, we use this accusation protocol. So imagine that, for example, we run check of computations, and worker I checks computations of worker J. Imagine if worker I is honest and worker J is Byzantine, and Byzantine client was computed something incorrectly. In this case, we cannot check. Others, they cannot check who is who. So we used a very simple idea. We just ban both the client who accused other client and who was accused. And since we assume the number of Byzantines is small enough, we will ban no more than 2 times B workers, where B is number of Byzantines, which is still okay for our purposes. Yeah, and the method that we use is called Bitartes GD. So it uses this Byzantine-tolerant all-reduced and then this step is followed by check of computation. So after each step, we randomly select 2 M workers. M workers will check other M1s and will not participate during the next step of computations. So which, so it allows us to continue the training, not to waste time. And in the paper we check correctness of the protocol, and therefore Byzantines might violate the protocol only a finite number of steps on average, and impact of each violation is upper bounded. That's it. So, and then we can also write the proof. I will skip that. So under some assumptions, what we do, we show, again, the first 2 terms are standard. The last term is non-standard, and it depends on the assumptions, but in any case, it has better dependence on epsilon, because epsilon is some small number, and we have epsilon squared instead of epsilon to the power 4. While prior works, they had epsilon to the power 4 here. And the main reason is that our protocol, it uses this, we can ban the Byzantines. This degree of freedom was not explored in prior works. And that's the first scalable server-free method that in the presence of Byzantines achieves the same communication complexity as parallel GD without any Byzantines. So when epsilon is small, this term is the dominant one, meaning that we converge as parallel GD in the ideal case for very small epsilon. And we also had some other results. I will also skip them. I also describe you idea behind the proof. So bound the bias and show that it will be active only during the finite number of steps. In the experiments, we tried 2 problems, like ResNet 18 on CIFAR10 and pre-training Albert Larch on Wikitext dataset. And we consider a setting when we have 7 Byzantines out of 16 workers, and considered standard attacks like sign flipping, which flips the sign of the gradient, random direction, label flipping, like we flip the labels into loss, and also delayed gradient attacks. So attackers send their real gradients delayed by 1000 steps. And we observe that actually our method, if we select the clipping threshold carefully, it can converge as good as baseline without any attacks. It's results for ResNet. And also, when you see when we activate the attack, we see this jumps, but then the method recovers. So it means that during this period we eliminate the Byzantines. So that's it. that I wanted to present today, and I will be happy to discuss this. Sorry, it took a bit longer, but I hope we will have time for the discussion.
Yeah, thanks a lot, Eduard, for the wonderful presentation. Maybe we just to kick off the discussion. The first question that I wanted to ask is about the scalability, because in the bounds that you showed, the rate, right, kind of the speed of convergence, it degrades. It seems to depend on the number of participants, right? Do you think that this is a fundamental limitation of the work, and have you observed that when the number of participants in this training process is increased, the training degrades, or it's maybe just like a worst case bound, and in practice we do not observe such a bad effect?
Well, it's a very good question. Indeed, in the worst case, we have this dependence on M, and also number M is number of clients that we select for the check of computation. It should be small. So in the worst case, it's like that. But in the experiments, I think we didn't have. But to be honest, we didn't try too many clients. So I think.
But here you show that you have 7 out of 16 clients, which is like almost half, right? So
so maybe in the situation, this is worst case bound. Maybe it can be improved, but I'm not sure. I didn't study the lower bounds in this setting, but let's say if number of Byzantines is small, we shouldn't have much of an issue. Let's say if here we had just one Byzantine client, I think this spike would be much smaller. Or is this one?
Yeah, seems like in this case, indeed, you have a very strong Byzantine attack, right? Almost half of the clients are trying to destroy the training.
Yeah. But then you see, they were detected very quickly. Unfortunately, in these plots, we do not report like the time when they were banned. But in our synthetic experiments, we modeled the behavior of Byzantines in the following way. So they start attacking, and at some point, let's say after 1,000 steps, and then they just continue sending incorrect information. In the real world scenario, they can do something smarter, let's say, but it turned out in our case that it was the most powerful attack, like to start at some point sending incorrect information and just continue until everyone is banned. This was the most powerful attack.
Yeah. Can I also ask a question? So about this accusation that we need to kick the one who accuses and another one.
Yes.
Can you explain, is there any workaround or like why do we need it? Why can't we check who is the liar? Because this kind of creates an incentive for the like honest participants not to accuse anybody, and creates an incentive to become a Byzantine actor.
It's a good question. So here we assume that honest workers, they do not switch identity. So if they join the protocol as good workers, they remain the same during the whole training. I think the main motivation was to avoid interruption. Like, let's say, I think this is well motivated when you have few, just a few Byzantines and a lot of good workers. Then this banning both is fine. Maybe later they can see we can do some further investigations, but during the training maybe it's it's not good, let's say, to stop all computations just to ask everyone to double check that computation. I think it's just related to impossibility of doing this on the fly.
Okay, so it's not like
fewer number, yeah.
It's not a fundamental restriction or limitation that we need to like ban both. It's if we design the training protocol such that really everyone will see, like if accusation occurs, half of the like participants can recheck who is a liar. If we do this, we can remove this rule about banning the tool, right? Although it will be
yes,
not
actually.
very...
Yeah, actually, I was not fully correct because sometimes workers, they can provide the proof, and in this case we ban only the one who was accused, and if the proof is correct. But in some situations, we cannot check what vector was sent. So, for example, here. The situation is the following. We have some worker I, so and it checks it receives the i's part of vector j from worker j and checks whether this number is indeed hash of that one. So, but since this part was seen only by worker I and j, and others, they didn't see it. So at this step, we even didn't do any check of computations. So we decided here to just eliminate both. And also when we do check of computations as well, let's say the one who checks the computation also can say that, okay, the hash is not the same as it was claimed. So, for example, if it does, if Byzantine does that, then we cannot also double check easily without recomputing that gradient. So that's why we also ban tool. Yeah.
Eduard, here you presented a modification of distributed SGD, right? And I was wondering whether this can be extended to the setting with like closer to federated learning, right? Where maybe we work in geo-distributed scenario, and there we would love to use, let's say, the local updates, right, in order to save on communication. Do you think it's possible to, combine these ideas with that scenario?
If you have public data, then I think yes, it's possible. Just in this case, I think the simplest solution would be to use not the stochastic gradients, but maybe the progress made by the client. Let's say each client, if they do multiple SGD steps or any method steps in between communication rounds, then in most of the existing protocols, existing methods, the clients, they just send the progress between the final point and the previous point. So we can just safely plug in it here. The only thing is that check of computations, it will take longer time. So we will need to check all steps. So again, it will take just one communication round, but it will take the time which clients spend on local computations. So this is the only difference.
On verification, and basically, also, right?
Yeah, on verification. But also what I want to say is that here we use this SGD type method. In fact, one can combine it with methods like Adam as well. anywhere where you do aggregation of the gradients.
Yeah, you just need to compute this with respect to updates, right, from the participants, and then perform any kind of optimizer update.
Yeah, but we don't have any proof because also for Adam we need to aggregate this, for example, second order statistics, and so we tried it. I think we just tried to run it, but we haven't analyzed theoretically. Because when you do robust aggregation of this like second order momentum in Adam, it will be also biased, and it's not okay. It's for the analysis. It's not very easy thing to analyze. Okay, I will go to the final slide.
Yeah, I mean, maybe with the new, I don't know, family of optimizers, this might be easier to do.
Yeah, so but the main idea here is just to ensure that okay, let me maybe show once again. Ensure that each step is like, we have some upper bound for the bias. Actually, we have also a version of the method that we use for like pre-training Albert Large. So we use, like, I think, clip as GD there. And when you have clipping in the method, then actually updates are bounded itself. So it's much easier to analyze such methods. And yeah, so, and also when we develop such method, it's important to ensure that each violation of the protocol, each deviation from the protocol can be checked if this client is selected to check for checking.
Also, are there any improvements since 2022 on this method? Maybe something like more than sentence clip, something else that has better guarantees?
So there were some improvements. Like yeah, it's a good question, but we haven't worked on that. Like on the extension of this protocol. But since then, many papers appeared. Let's say, centered clip is not the only one. Like it's not the only existing robust aggregation rule. Yeah, so I think I think it's possible to modify it as well. To use instead of center clip, to use, let's say, this protocol called fixing by mixing by the group of Rashid Guirawi. Sorry for pronunciation, but it's the paper is called fixing by mixing. I think it AS Stats 2024 or 2023. Should be, yeah. And they proposed also a nice aggregation rule. And also in this paper and the follow-up by Karimi Reddy et al., they proposed a fix how to fix median, cram, and coordinate-wise median to make them robust.
So the general idea is the same, is like, if there is this property of robustness is satisfied, and we can like limit bound the effect of the attack, and also we do the computation checks, then probabilistically we will find attacker at some point, and the effect on the training will be finite. And it doesn't matter what aggregation rule is, it's important that it satisfies the condition of robustness, right?
Most likely, yes, but the part that I'm not sure about is this one. So because for centered clip we have this nice equation, so we can check it in random directions and so on. Yeah, I need to think about extension to other aggregators. Yeah, thank you. It's a very good question.
Oh, one more thing. I wonder, you were talking about the all reduce, and you mentioned butterfly all reduce. So is there any specific about this particular protocol? Is like it's somehow makes it more vulnerable because nobody sees this like fifth part of the vector. Can this method be extended to something like maybe ring all reduce or excessive if we increase the number of communications, for example, twice and make the more robust butterfly or reduce something like that? So what's the criteria for choosing this all reduce method?
Yeah, it's a good question. So as far as I understand, in ring all reduce, if you have one Byzantine, it can spoil the whole vector, not just one part. So maybe that actually I think that was one of the main motivation. So here you have one-to-one communication, so it's like more information to check, like easier to check and easier protocol in a sense. So I think mainly because of that we focus. But you're right.
Yeah.
So we should have explored also other options. But as I said, like I think ring all reduced, for example, it seems to be more vulnerable because here at least in a sense, even if this worker is Byzantine, here good client used centered clip and here the client used center clip. So at least this part of the vector was good. So at least we updated something, some part of the model correctly, let's say robustly. And this and the first part was just arbitrary.
So
Updated
it's like
arbitrary but bounded.
Got it. So it's like with this all reduce method, we isolating the possible like problem subvectors. So we can isolate because this is how it works. In ring all reduce, everything get mixed, and maybe it will be harder to distinguish.
Yeah, because everyone broadcast to the next neighbor each time the part of the vector. Yeah.
Okay, cool.
And yeah, also another thing is that here we collect all the vectors and then apply a robust aggregation. So it's for example, averaging or summation, they can be applied like sequentially, but these aggregations they need all vectors first, and then we do computation. So it's another restriction. Yeah.
Okay. Yeah, I think we are good on time. Yeah. Discussion
So
turned out to be
also,
even.
you can also check the paper. It's available, like the updated version is available on archive and also at ICML. We have some better pictures than those I have here, but yeah, please check the paper for further details.
Yeah. Thank you very much, Eduard. Yeah, very nice presentation. Wonderful insights. Especially interesting. Nowadays when the field of distributed collaborative, decentralized training is being more and more kind of developed and popular. A lot of relevant ideas, I think, for that field as well. It's a nice, combination between like this optimization, robustness, and some security aspects, right? Like this kind of cryptographic checks. Very nice work.
Yeah, thank you, Eduard. Actually, I liked how you structured it because you like during the presentation you were presenting more problems, and it kept me on my toes. Like, oh, is this solvable? And then you're like, yeah, this is solvable. And then, but this problem is here. So I was having the question: is this kind of training like solvable for the whole presentation until you like covered all the problems?
Yeah, thank you. It's my pleasure. But yeah, I think number of slides is a bit more than I used to. But yeah, in 2021, I tend to have more slides. Now I made shorter presentations. Yeah.
That's okay. Yeah. I think you managed it well. So yeah, thank you very much once again. Thank you everyone for attending. Yeah, we hope to have more of this kind of seminars in the future. Yeah, so have a nice rest of the day.
Yeah.
Thank you.
Bye.
Bye.
Thank you.